Hello. In this video lesson, we'll talk about chromatography. Chromatography is one of the largest disciplines of physical methods of investigation. It includes various types of chromatography, and general information is quite much. And besides this, chromatography includes HPLC, gas chromatography, column chromatography, thin layer chromatography. And therefore, this topic is divided into three parts. In this video lesson, we'll talk about chromatography in general and some information on thin layer chromatography and column chromatography is provided as well. And in other two video lessons, we deliver some info about HPLC and gas chromatography. And I recommend you all to watch two other video lessons on chromatography, HPLC and GC. So you might have them useful as well. Here we go. Okay, first of all, we need to understand what chromatography is. The term chromatography designates several similar techniques that allow the separation of different molecular species from a mixture, and the separation of mixture can happen in different, let's say, status by using different molecules. Applications of chromatography are numerous and can be related to laboratory or industrial practice. In industry, chromatography is very efficiently used. The molecular species subjected to separation exists in a sample that's made of analytes and matrix. The analytes are molecular species of interest to be separated, let's say, and the matrix is the rest of components in this sample. So here in this figure, we can see that inside, for example, if this is a column chromatography, inside a column, we know that there is matrix that enables the separation of different compounds inside it, and they are washed, let's say, eluted with different solvents, and this is used to designate the solids. And the compounds, active compounds, I mean the analytes, are separated from each other by the elution of solvents. So this is about how the chromatography is carried out, how the chromatography happens. Sorry. Okay, for chromatographic separation, the sample is introduced into a flowing mobile phase that passes through a stationary phase. The stationary phase retains stronger or weaker different passing molecular species and releases them separately in time back into the mobile phase. Here in this figure, we can see that in an example of column chromatography, we can see that this is the stationary phase inside which the compounds are separated into different, let's say, fractions, and the upper side is termed, let's say, mobile phase. Here inside, okay, here the compounds, the extracts to be separated is loaded. So as time goes by, as indicated here in other four column images, we can understand that the compounds can be separated from each other as time goes by. So what is the fundamental basis of the separation? The reason how the separation in column chromatography or other types of chromatography happens is explained with the affinity of the sorbent. Yes, we called in the previous reaction matrix, with the sorbent and the compound inside the extract, let's say, to be separated. So the higher, stronger interaction between the sorbent and the compound, the later, let's say, elution, the weaker interaction between the compound and the sorbent, the faster elution. Okay, this is the point. The lower interaction, the faster elution, the higher interaction, the slower elution. Okay, when the mobile phase is a gas, the chromatography is indicated as gas chromatography. When it is liquid, it's indicated as liquid chromatography. So in this example, this is a column chromatography. In this column chromatography, the mobile phase is liquid, so this is termed as liquid chromatography. If the mobile phase usage is around gas, so we call it gas chromatography. Okay, and there are other types other than liquid or gas chromatography. Those other types include supercritical fluid chromatography, yeah, counter current chromatography, or electrochromatography. Uh, I recommend you to find some info on YouTube or on Google and know about the differences among these types of chromatographies and compared to GC and LC. In our video lessons, we haven't covered these three chromatography types. Okay, and based on different factors, chromatography can be classified differently. For example, based on the beds, we can divide chromatography to column chromatography and planar chromatography, which is sub-qualified as paper chromatography or thin layer chromatography. We are going to talk about thin layer chromatography. Just as additional information, let me remind you that in column chromatography, we use the elution vertically from upside down, and in planar chromatography, the mobile phase goes up. This is one of the main differences between column chromatography and planar chromatography. And based on the physical state, uh, the chromatography can be qualified as gas chromatography or liquid chromatography. Yeah, and liquid chromatography can also be qualified as a high performance liquid chromatography or supercritical fluid chromatography. There are different approaches about the qualification, about the classification of chromatography. That's why in some cases we can see some discrepancies in this example and in these examples. Okay, and based on the separation mechanisms, the chromatography can be classified as affinity chromatography, ion exchange chromatography, and gel filtration chromatography. In affinity chromatography, the power that causes the separation of different compounds is affinity between the matrix and the compounds in the extract or in the separated part, right? That affinity, for example, one type of affinity is the affinity between agarose and lectin, for example. Lectin, for example, a protein of plant origin, is tightly linked to agarose. That is one of the well-known examples for affinity chromatography. And in ion exchange chromatography, the power that holds different compounds differently um, is based on charge interactions, like charge interactions between carboxyl groups and primary or secondary amine groups, or sulfur groups with some, let's say, cations, some factors like that, some examples like that. And gel filtration is around the filtration based on the sizes. So it is sometimes termed as a size exclusion chromatography. Yeah, so based on the separation mechanism, we can separate the chromatography as affinity ion exchange chromatography and gel filtration chromatography. And here we can see the differences between the types of chromatography from another corner. Okay, Some authors considered these four types of chromatography, and the first one is absorption chromatography. In absorption chromatography, the mobile phase can be gas or liquid, and the stationary phase is solid, like matrix are always in their solid state, and stationary phase support can be column or planar layer like paper or thin layer chromatography, let's say, tools. And in absorption chromatography, the techniques that uses gases, mobile phase, and stationary phase solid is termed as gas-solid chromatography, and the one between liquid and solid is termed liquid column chromatography, or high-performance liquid chromatography. Again, about HPLC, we provided a separate video explanation. Okay, and if the mobile phase liquid and the stationary phase solid, and we use a planar layer, and we call it thin layer chromatography. We are going to talk about it further in a few examples. Okay, and partition chromatography. In partition chromatography, mobile phase can be gas or liquid, and the difference between absorption chromatography and partition chromatography is about layer state. Here it is solid, and the stationary phase in partition chromatography is liquid. Stationary phase support can be column and planar layer chromatography items. Yeah, and partition chromatography can also be qualified as liquid chromatography or high performance liquid chromatography, or paper chromatography as indicated here. Okay, and ion exchange chromatography based on the exchanges of ions, and in this chromatography, mobile phase can be liquid, stationary phase can be resins, yeah, that provides the exchange of ions, and it is supported with columns, and we call them ion exchange chromatography. And permeation chromatography, mobile phase is liquid, sorry, and the stationary phase is polymer matrix, yeah, and it is supported with column, and they are named size exclusion chromatography, and abbreviated as SEE. GPC, sorry. Okay, now we are going to talk about TLC, thin layer chromatography. In thin layer chromatography, we can see this kind of separation. The tools that's shown here can be the glass on the surface of which, okay, there is a layer of, for example, silica gel or aluminum oxide. Yeah, aluminum oxide or silica gel or other sorbents can also be layered on the surface of some flexible iron-made materials. Like other chromatography techniques, thin layer chromatography depends on the separation principle, and the separation relies on the relative affinity of compounds towards both phases. The compounds in the mobile phase move over the surface of the stationary phase. As indicated here, again, the mobile phase is located at the bottom of the glass. As we install the TLC on the inside the bottom, okay, the mobile phase starts to go up, so the separation on the surface of the TLC plate can happen. The movement occurs in such a way that the compounds that have a high affinity to the stationary phase move slowly, while the other compounds travel fast. Again, here the separation can be based on the affinity between the stationary phase and the mobile phase, including the extract, for example, including the mixture of compounds. The higher affinity between them, the lower, let's say, movement. Yeah, the lower affinity between the matrix and the compounds to be separated, the faster action with the solvent, with the eluent. Okay. Therefore, the separation of the mixture is attained. On completion of the separation process, the individual components from the mixture appear as spots at respective levels of the plates. The characters and nature are identified by suitable detection techniques. So by using thin layer chromatography, it will be possible to separate the compounds based on the comparison with some standard compounds. It will be possible to identify or at least suggest the similarity between the standards and one of the spots which is close in the line. So this kind of comparison can be done, or those spots can be separated and be further analyzed by using HPLC, for example, or mass spectral chromatography or some others. Okay, this is about how it is done. And here we can see how it can be started and carried out. Here, for example, if we have thin layer chromatography plate, like glass one or the iron made one. So a line is drawn, a point is appointed, and there slowly, by using this kind of low volume syringe, we can we can here uh, send out the extract in high concentrations as possibly. So then we can put it in a glass, something like that. It will be better if the glass is covered. Not this kind of glasses are recommended in order to provide the constant, like, let's say, the constant ratio of the volume of the eluent that could be more volatile compared to others. It is better to provide the system to be protected from the air. Okay, so we install TLC plate into it, and the mobile phase should be lower, or the exactly should be a bit lower level of this line, or the same. So then we can expect the extracts to be separated by going up by getting washed with the eluent. Otherwise, if it's lower, by the time it gets up with the eluent, some amount could be could be mixed with the solvent inside it, so the separation may not be very appropriate. So here we can see how the separation can happen as time goes by, as the distance between the starting point and ending point is, let's say, longer and longer. So we can see the more and more strict differences between the compounds, and as indicated here. Okay, so we can end the separation as the solvent reaches this level. Okay, and here we can see some other results about TLC. TLC is an affinity-based method used to separate compounds in a mixture, as was described earlier. TLC is a highly versatile separation method that's widely used for both uh, qualitative and quantitative sample analysis. TLC can be used to analyze virtually any substance class, including pesticides, steroids, alkaloids, lipids, nucleotides, and glycosides, carbohydrates and fatty acids. The point how it can be used as qualitative. Okay, we can use some standard compounds together with the extract. So based on the RF pointers, we can find out about the similarity of the structure or let's say, we can claim the same structure of the compounds. This can be considered as qualitative analysis, and quantitative analysis can also be carried out. We are going to see in the next pages. And based on the variety of the composition of a mobile phase, it will be possible to separate and identify the compounds belonging to different compounds, whether they are pesticides or steroids, alkaloids, lipids, yeah, nucleotides, carbohydrates, fatty acids, glycosides. Yeah, if the compounds are glycosides or carbohydrates, which are more, let's say, hydrophilic, so the mobile phase can be prepared with by using the solvents with higher, let's say, hydrophilicity or polarity. So then this kind of compounds can be separated from each other, let's say, more effectively. And the inclusion of hydrophobic compounds is also significant as well. Or vice versa, for the fatty acids, we can include some solvents like hexane or ethyl acetate, yeah, um, or acetyl, yeah, to provide them to be separated from each other. I mean, for compounds with higher hydrophobicity, with lower polarity, we need to provide the mobile phase with lower polarity as well. These are the points that we have to pay special attention to. This thing is can be found by reading the reference literature. So you can find from NCBI as many as possible um, publications about about TLC and some new approaches of TLC that we are going to talk here. This is high-performance thin layer chromatography, which is abbreviated as HPTLC. It serves as an extension of thin layer chromatography. This is a kind of updated type of TLC. It offers robustness, simplicity, speed, and efficiency in the quantitative analysis of compounds. This TLC-based analytical technique enhances compound resolution for quantitative analysis. So this is not only about, let's say, using some techniques like UV or updated, let's say, mechanisms of separation, but also the sorbents are expected to be smaller, so then the resolution can be let's say, of higher, let's say, efficacy. Some of these improvements involve employing higher quality TLC plates with finer particle size in the stationary phase. So finer particle size is very significant in achieving efficacy of high performance thin layer chromatography. It leads to improved resolution, as we talked, and additionally, the separation can further be refined through repeated plate development using a multiple development devices. So, in order to achieve this kind of efficacy for extracts, as indicated here, the particles that are used as a sorbent for thin layer chromatography should be, let's say, of lower size and higher volume. The lower size, the higher volume can lead to a more effective separation, as indicated in this photo. As a result, HPTLC provides superior resolution and lower limit of detection. So if the concentration is lower by using HPTLC, we can reach some this kind of separations as well. And here we can see that if the extractors are located on the surface of the TLC plate in a wide, let's say, dimension, so then the lines can be wide enough like this. If it is small, so then we can expect something like this. Okay, based on the concentration, we can use small size TLC plates, or if we have some amount like grams of, for example, some compounds after reaction or the extractors themselves. So then we can use this kind of higher volume cameras that can enable us to separate the gram extracts or compounds after reaction to separate. Separation and purification from milligram to gram quantities can be done by using this kind of high volume cameras. The thicker layers than classical TLC for higher sample loading volumes. They are rapid and cost-effective methods for identification and isolation of compounds from a reaction, and they are identified as qualitative evaluation offline. There is no any kind of chances to compare them with kind of online, let's say, databases. Because these methods do not enable us to link them with online tools. And here in this example, we can see how the extractors can be compared with each other. Here we can see the first compound is caffeine. Okay, which one? I think this one is caffeine. The second one is chlorogenic compound. Actually, it's three. Or the caffeine is not indicated here, or here caffeine is indicated. The second one is chlorogenic acid. The third one is rutin. The fourth one, rutin and chlorogenic acid. Yeah, rutin and chlorogenic acid. And this one is chlorogenic acid, and this one is rutin. And this one is the mixture caffeine is not visible. Okay, by using thin layer chromatography, by using PEG and PR mixture, and under the UV at 366 nanometers, this kind of images can be obtained. So then it will be possible to compare the extracted with each other. I mean, the extract in the third in the seventh position can be considered to differ from others with the composition of routine. So then by using faster approaches, something like this, it will be possible to know about the comparative efficacies of the samples and or extracting methods by comparing those extractors with others. So in industry, in the pharmaceutical industry, or in cosmetics industry, thin layer chromatography, modern updated versions of thin layer chromatography can be effectively used as indicated in these photos. Here we can see its UV spectrum, UV figure at 254 nanometers, and here 366 nanometers. And this is another example about the stability testing of combination of herbal drugs in capsules at 25 and 60, 25 centigrade and 60% of RH. And here we can see some comparison within 0 month and after 16 months. Yeah, this is a very good example about the stability test within 18 months. Okay, this may not be very, let's say, comparable based on the intensity of the color, but this one carried out after 12 months shows some, let's say, similarity between here. Okay, they are close to each other, they are close to each other, and this color existing and this color existing, and here we can see the presence of this color, but this color may be lowered a bit. So by using this kind of comparisons, it will be possible to see um, the effects of TLC for stability testing as well. And this is another example of carried out on lavandin flower. Yeah, 2 years, 1 year, 0 year. Yeah, 0 year, 1 year, and 2 year. Here we can see in 2 years this compound either destructed or can be considered as not stable, and others remained. And here we can see the differences as well. So thin layer chromatography can be used for such purposes as well. And now we are going to talk about column chromatography. Column chromatography is very effectively used for the separation and isolation of proteins and peptides and polysaccharides, so glycosaccharides. Uh, uh, some approaches are effectively used for the identification of new peptides as well. We talked about this figure. This is a good example for column chromatography. Here, this is stationary phase, loaded phase, yeah, mobile phase flows down and causes the separation of compounds based on their interaction with the matrix, with the sorbents. The higher interaction between the compound and the matrix, the slower, let's say, elution. The weaker interaction, the faster elution, as we talked earlier. And here we can see similar, let's say, we can make similar conclusion. The low affinity, the lower interaction, the faster elution, the high affinity, yeah, the higher interaction between the compound and the sorbent. So the elution is slower, as we talked. Okay, here in this table we can see about the absorbents that are used in ion exchange chromatography. Ion exchange chromatography is classified as cation exchange chromatography and anion exchange chromatography. In anion exchange chromatography, we use cationic adsorbents which have positive surface as indicated. The charged surface are provided, charged functional groups are provided on the surface of the molecules. Here we can see one example, like a typical material, like chitosan. Yeah? Chitosan and chitin are the natural polysaccharides holding different ratio of amino groups or acetylated amino groups. Chitosan, chitin is the second most abundant polysaccharide after cellulose on the planet. It is the exoskeleton of insects and the protecting polymer of the fungi. So this is very widely spread in the nature. So they can be isolated and well used in chemistry and industrial processes. Since it has amino groups on its surface, it can be effectively used to hold negatively charged molecules in the molecule. Okay, this is the point that we have to pay, we have to understand. Here is another example, DEAE. diethyl aminoethyl cellulose, diethyl aminoethyl derivative of cellulose, and it also has positively charged nitrogen on its surface. So this is another polymer that is widely used as anion exchange sorbent anion exchange matrix. Okay, here we can see anion exchanger. Chitosan is anion exchanger. DEAE is another anion exchanger. Okay, and here we can see one example of cation exchanger. We call it carboxymethyl cellulose, sodium carboxymethyl cellulose. As it is kept in a water condition, sodium is isolated, ionized. I mean, the functional group is ionized and it turns to carboxyl group. So then this carboxyl group can be effectively used to hold positively charged ions like the ions of heavy metals. So then they can be, let's say, removed from the system. They can be kept in the system by using carboxymethyl cellulose, or similarly, nitrate or phosphate ions can be kept uh, in the column chromatography that uses DEAE, diethyl aminoethyl cellulose, or chitosan. So the principle of anion or cation exchange chromatography is based on the charge-charge interactions between the unlike charges plus and minus. This is not only between charge-charge interactions. Anion exchange or cation exchange chromatography can also be used for charge dipole interactions as well. It's not exactly necessary uh, for this type of chromatography to have charge-charge interactions. If there is charge dipole interaction, it can also be effectively used to hold those compounds with hydro, let's say, dipole level. Okay, so this is about ion-ion exchange, ion exchange chromatography. Sulfonated resins, carboxymethyl cellulose, graphene oxides are used in anionic, are used as anionic adsorbents. Okay. Let me remind you one thing. Okay, adsorbent, surface charge. Okay, so adsorbent is used for the sorbents that absorb the compounds on the surface, and absorbent, AB, is used for the sorbents that sorb ions not only on the surface but also inside it. So this is the difference between adsorbent and absorbent. Okay, again, these are examples of adsorbents, the surface of which are provided with functional groups. For example, in this case, the surface of this compound was provided with functional groups like amino group or diethyl aminoethyl derivative groups. So then they can attract minus charged molecules like this. Yeah, and this example, the sorbent that was provided with negatively charged groups like sulfate group or carboxyl group, they they are highly effective to attract positive charge. So this kind of sorbents can be effectively used to hold heavy metals in water, let's say, samples. Okay, and this is another example. Negatively charged analyte can be held by positively charged anion exchange stationary phase, and vice versa, positively charged analytes like cations could be held on the surface of cation exchange stationary phase particles, like the one provided with sulfonate group or carboxylic group. And these are about the technical specifications of ion exchangers. In a strong acidic cation exchanger, here we can see the sodium ionic form, and as strong basic anion exchanger, here we can see chloride ions, and the functional groups can be for sodium as sulfonic acid, as talked in the previous pages as well, and for chloride ions that could be quaternary amine groups, or other amine groups that we talked in an example of DEAE or chitosan. And the structure in both cases, yields and total capacity differ from each other. Bed sizes could be similar, flow rate could be similar, and they are regenerated by using different solutions. For the regeneration of acidic cation exchanger, okay, we use sodium chloride, and for the regeneration of strongly basic anion exchanges, we use sodium hydroxide. And the regenerant level can also differ from each other. So these are about the technical specifications of ion exchangers. And now we are going to see two examples of sorbents that are used in column chromatography very much and very effectively. The first example is cephorose. Cephorose is a cross-linked type of agarose. Agarose is obtained from the seaweed. The cephorose, the name cephorose was taken from separation of pharmacia and agarose, since it is used for separation, produced by a Pharmacia, Swedish company, and made of agarose. So the name cephorose was pondered, generated. It is highly effective for the separation of proteins and peptides. Cephorose is a registered trademark of Citiva. And here we can see the differences in A, B, and C examples. Here it is in low concentrations, and in B figure, here we can see high concentration of the agarose with low degree of cross-linking. If the degree of cross-linking is high, so the pores can be, let's say, more stable, so they can be more effectively used, let's say, for the separation of smaller sized proteins and peptides. Here we can see the differences between the cross-linking, let's say, levels. The concentrations in both cases is high, but here we can see low level of cross-linking, and here high level of cross-linking. This kind of low level and cross-linking agarose can be used for higher, let's say, molecular levels of molecular sizes of proteins, and this one, and since it is more stable based on the covalent bond in cross-linked points, it can be effectively used for the separation of small-sized proteins as well. So this is about agarose polymer. And here we can see agarose beads after staining with bis A and C dye. And here we can see that this kind of cross-linking is provided in agarose. I would like you to pay your attention to this inner molecular circle between carbon oxygen and carbon oxygen in this case. So we can understand from this figure, when it is cross-linked, that oxygen involved in this, that oxygen in the form of inner circle is involved in the cross-linking as indicated here. And this is a scanning electron microscopy image of the cross-linked agarose. Based on the separation, based on the pore sizes, uh, the agarose can be effectively used for size exclusion chromatography, yeah? And or if it is or if the saccharose uh, is found as affine to some polymers, like, for example, lectin, yeah, it can be used as a affine chromatography sorbent as well. And based on the size resulting from the different levels of cross-linking, again, it can be used for size exclusion chromatography as well. And here we can see the different, here we can see the linkage between the agarose concentration and protein exclusion limits, the higher concentration and the lower, let's say, kilodalton is indicated here. The point we need to understand, if the size of the agarose is smaller, this is not about the cross-linking, this is about the size. If the size of the gel is smaller, so then the surface is higher. The higher ratio of surface to volume leads to higher binding capacity. If the binding capacity is higher, so the separation can be more effective. And here we can see high size and low surface to volume ratio. Yeah, here lower ratio of surface to volume. So this kind of gels are used for viscous media. They can be used for the purification, for batch purification. So based on the size here, we can see different purposes that they can be used. The higher ratio, the smaller size leads to utilization for effective separation, but the higher size and lower surface is used for batch purification. Overview of different agarose resins, bead sizes and advantages of different sizes. The smaller beads have higher surface to volume ratio. Bigger beads, on the other hand, allow for higher flow rates, which makes them more useful for viscous cell media or batch purification or gravity model. Okay, then the second sorbent we can talk now is Cefadex. Yes, Cefadex is a cross-linked dextran. This is the structure of dextran. I think it is also obtained from the seaweeds. It's not written here. Okay, the point that we have to understand that dextran has alpha 1,6 and 1,3 glycoside bonds. Here we can see 1,6. Is it 1,6? It's here. This is alpha 1,3 bond. Okay, the first position, and here compared from this one. Okay, 1, 2, 3, 4. Okay, 1, 2, 3. Sorry, 3. This is 1, 2, 3, 1, 3 alpha bond, and this one is 1, 6 alpha bond. So it has two different glycoside bonds in dextran. So it is also cross-linked, and the cross-linked material of dextran is termed Cefadex. It is also produced by Swedish Pharmacia, one of the largest exporters of chromatography tools and solvents. Yeah, this is also very effectively used for the purification and isolation of protein and peptides in research purposes. And here we can see characteristics of different types of Cefadex. They are marked as G10, G15, up to G200 or G200 superfine. G150, G200 were stopped, I think, to produce. Okay, they were discontinued products. And the point that we need to understand is the type termed G uh, with low size and low cross-linking level is used for the fractionation of globular proteins with smaller, let's say, uh, size, 700 atomic mass unit or 700 Dalton. G15 can be used for peptides with lower 1500 Dalton size. Yeah. And G25 is used for the peptides differing by the molecular weight uh, from 1000 to 5000 is used. And G15 is used for the proteins and peptides that differ. Let's say G50 is used for polypeptides differing with molecular weight from 1500 to 30,000. Yeah. And accordingly, G75 from 3,000 to 80,000 Dalton, or G75 superfine is used for the separation of peptides from 3,000 to 70,000 Dalton. The point we need to understand is that in the superfine marks, the maximum level of the protein separation is lower compared to their counterparts without superfine, let's say, type model. Here in G75, the maximum separation allowance is 80,000 and superfine 70,000. In G100, 1,500, 150,000, sorry, and G100 superfine is of 100,000, and similar tendency between G105 superfine and the next one as well. So this is all for now. I hope this information will be useful for you. Again, uh, if you want to know about HPLC and GC-MS, I highly recommend you to watch uh, our videos on HPLC and GC in this playlist. And I hope you to support us with your likes so that our video lessons can reach a wider audience. And I express my thanks. Thank you for watching. Have a good day. Bye.